Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book. And I'm on section 3.2, which is on irrational numbers. And I just got through talking about square roots and nth roots. Today I'm going to talk about roots of polynomial, which are more general. These are the more general types of roots, but they're all what are called algebraic numbers. There's also numbers called transcendental numbers. I'm not going to get into that today, I don't think. But anyway, let's begin. This is going to be a pretty short lesson. I only have one page to show you. I think I kind of talked about most of this yesterday, actually. So, polynomial, in case you don't know, it's a special type of function. It's a function where all it's just a sum of powers multiplied by ordinary numbers known as coefficients. So a general polynomial would have the form I show on the top line, f of x equals a sub n, that's just a number, a sub n, times x to the nth power. N is what's called the degree of the polynomial. And then we keep going down. The next one will be a sub n minus 1, x to the n minus 1, plus so and so, and then you have like a 2x squared plus a 1x plus a 0. You're just supposed to imagine you can plug in any numbers you want for these things. So, for instance, quadratic polynomial would just be a polynomial with degree 2. That's ax squared plus bx plus c, where a, b, and c are ordinary numbers. You probably learned about these in high school, like 3x squared plus 5x plus 6, or 3x squared minus 5x plus 8. And you probably learned how to factor them. Sometimes you can factor them into rational terms, but most of the time you can't. And you probably also learned a very useful formula called the quadratic formula, which I wrote on the bottom of this slide, just to remind you. If you have a general quadratic polynomial, ax squared plus bx plus c equals 0, so you want to find all the roots to that polynomial, then it turns out that the quadratic formula tells you what the roots are. They're just given by this formula. The roots are minus b plus or minus the square root of b squared minus 4ac. That's what's in the numerator. And then the denominator is 2a. Pretty nifty formula. And not too hard to remember either. And the quantity inside the square root, b squared minus 4ac, that's a very important quantity. That's called the discriminant of the quadratic polynomial, and it tells you how many roots there are and whether the roots are real or imaginary. Just to refresh your memory on that, if the discriminant b squared minus 4ac is positive, that means you have two real roots to your polynomial. The quadratic polynomial, if you graph it, it always looks like a parabola. So you should be thinking about, I didn't show a graph here, but if you graph this, this quadratic polynomial, it would look like a parabola. If a is positive, then it's concave up. It looks like a cup kind of. If a was negative, which you very rarely see, it would be concave down. It would look like a hill, but you don't usually see that. But you could get that, and then you'd see where it intersects the y-axis or the x-axis rather. And the two values of x for which it intersects the x-axis are the roots to that polynomial. So if the discriminant is positive, that means that the parabola dips below the x-axis. That means that the minimum is less than 0, so it has two roots. And probably would have helped if I showed some pictures here, but I think you can kind of picture in your mind. You probably learned this already. If the discriminant is 0, that's kind of a special case. That means that there's only exactly one root, and the root is the vertex of the parabola, because that turns out to be the value of y corresponding to the vertex is 0. The discriminant's 0 means the square root 0, so the roots are just minus b over 2a. It's a double root. It's called a double root. Negative b over 2a. And if the discriminant's negative, then you get no real roots. So you'll get a negative quantity inside the square root. That's what's called an imaginary number. I haven't talked about complex numbers yet, but this is an example of a complex number. It turns out you always get two roots for any quadratic polynomial over the complex numbers. They might be imaginary. Or you might get what's called a double root. If the discriminant's 0, that's a double root because it kind of counts like two roots, even though they're both the same root. And similarly, there's a very important result in mathematics called the fundamental theorem of algebra, which says not only for quadratic polynomials, but for a general polynomial, say of degree d, that's what you usually use for the degree, there's exactly d roots, d complex roots, counting multiplicities. So another way of saying that is that the complex numbers are algebraically complete. You never get a root of a polynomial with complex coefficients where it's not complex itself. That's what we mean when they say it's algebraically closed. I'm really jumping the gun here. And I think I should just say one more thing. We have this nice formula called the quadratic formula for solving the roots of a quadratic polynomial. Uh, and linear is trivial. I mean, linear is just basic algebra. But what about cubic and quartic? Well, it turns out there are formulas as well for cubic and quartic. They're very, very complicated formulas. They're almost impossible to memorize. They're easier to derive than to memorize, it turns out. And this was done a long time ago. I mean, I don't know when the quadratic formula was discovered. I think in ancient times. I think I remember learning that the Babylonians, who were some of the greatest ancient mathematicians in the world, they actually discovered the quadratic formula. I think around at least 2,000 years ago, maybe closer to 3,000 years ago. The Babylonian civilization, I think, kind of flourished mainly around 1000 BC. So my guess is that the quadratic formula is about 3,000 years old. Very, very old formula. It's been known for a really long time. And I think it was even known in Europe during the Middle Ages. There was some knowledge that wasn't forgotten. And I'm pretty sure they knew about the quadratic formula. It might be wrong. I don't know. But the cubic and quartic, there's a really interesting history about those cases. There were a handful of Renaissance mathematicians. I think the leader among was a guy named Girolamo Cardano. He also was the inventor of probability theory. Very, very famous mathematician and a gambler. It turns out there were several mathematicians who were also gamblers. And I guess the reason they were interested in probability theory because they wanted to know the theory of how to win at gambling. Cardano, I think, was the leader among that. But among other things, one thing Cardano did, and I think some of his friends too were also gamblers. There was Ferrari, and there was a few others. I can't remember. Vieta, I think. They were mostly Italian. And they were able to derive the cubic and quartic formulas. For which, those are formulas that will give you all the roots, whether they're real or imaginary, of cubic and quartic polynomials. Pretty amazing formula. Very, very complicated formulas. I don't talk about them in my book because, like I said, they're really hard to derive. You'll practically never see them used. But what I think is interesting is that there do exist formulas for computing roots of cubic and quartic polynomials in terms of radicals. They're all radical expressions, meaning that they all involve nested nth roots. I think the biggest root you get is a fourth root. You get cube roots and fourth roots. You don't get any higher order roots. But then you might think, well, what about higher degree? What about degree 5 or higher? I think I talked about this yesterday. For I think a couple hundred years, there were a lot of mathematicians who were trying to figure out how to solve quinic, how to solve degree 5 or higher. And I think they mostly concentrate on degree 5 because that would seem to be the simplest case. But finally, by the early 19th century, it was proven that there is no such formula for degree 5 or higher. In general, there are special cases for which you can solve the roots of a polynomial of degree 5 or higher in terms of radicals. For instance, x to the fifth minus 2 roots are just the fifth, one root is just the fifth root of 2, obviously. But that's kind of a trivial case. In general, you can't do it. And the proof was very, very complicated. The proof involved the area of math that wasn't even invented until the early 19th century. As a matter of fact, I think in Beale and Galois invented this area of math called group theory, just to try to solve the quintic equation and higher order equations, and they proved that they're unsolvable in terms of radicals. But then group theory turned out to be a much richer area of math that has a lot of applications that go way beyond just finding roots of polynomials. But that's how it got started. So I thought I might mention that. I do talk about group theory, I think later in volume one. I believe it's chapter 6 is all on group theory. I just gave you a little bit of heads up on group theory. Beautiful area of math. It's an area of abstract algebra. It's kind of conceptually difficult, but there's some very simple groups to work with. I think when we get to group theory, it'll be fun because I actually think that kids in elementary school could learn some of the basics of group theory, and they probably should be taught it in elementary school. I'd say around the same time you start learning algebra, ordinary algebra, because it's not really that hard and it's really useful and it has really important applications in physics as well. And there's a result called Noether's theorem, which is a very powerful theorem that says that for every symmetry of the universe, there's a corresponding conservation law. So that explains conservation of energy, momentum, and angular momentum, among other things. I'm really jumping the gun here, but I just thought I'd give you a little heads up on group theory. And the reason I mentioned group theory is because it is a technique for solving roots of polynomials of degree 5 or higher. I think you can still solve the roots. You just can't write them down using radicals, but you can solve them by other means. Anyway, that completes my video for today on roots of polynomials, which are all irrational numbers, by the way. The real ones are all irrational. Anyway, thank you for watching. Long live math, and I'll see you guys next time. Bye.